are moving on to the sense of hearing today. If you want to go in your textbook, it is there on page 282. Thank you, Hannah, for always being my textbook provider. Page 282, we're talking about hearing, the sound of my voice. Ooh, I forgot that I had something I was going to do with you. If you are watching on the video, you will see me as I try and do this. Are you comfortable that hearing is a super complex thing? Shh. Very complicated. I want you to listen to this. Don't look here, though. Does anybody recognize this song? Very piano heavy.
Yeah.
Don't say anything yet. I'll give you a clue. 90s grunge rock. Good. Don't say it yet. Maybe this will help. Chorus. Okay, so now let me try this. Maybe you recognize this a little bit more. Okay, this is hardcore 90s stuff. That's Nirvana, right? Smells Like Teen Spirit. The previous was the same song, but it was Tori Amos. She was a piano pop player back in the day. How did those of you who got that, how did you know? Those are two very distinct sounds, right? The lyrics were the same, good, right? You could kind of, sort of, but they're significantly different, right? The pitches were a little bit different. Right? Certainly the tempo was different. And yet your brain said, oh wait, I know that song. I would bet that none of you had ever heard that version by Tori Amos before. It wasn't very famous at all. Your textbook actually was the one who clued me into this. The very first page of your textbook talks about this. But how your brain interprets those auditory signals, it's quite an impressive thing. Music especially hits that really well. So let's talk about how this system works. Let me punch back up here what we've got going on here. So kind of three components of our ear: the outer or external, the middle, and the inner, right? And the ear is working with two senses. We're going to focus on hearing first, then we'll go to the second one. The first is hearing, the second is what? Balance, equilibrium, right? So the outer part of your ear is what we call the auricle, A-U-R-I-C-L-E. That's what this thing that hangs out that holds our glasses up and we decorate with earrings. That's the auricle, okay? What's the point of that auricle? To direct sound where? Into the ear. Particularly, what do we call the opening that goes into your ear? The external auditory meatus. Now this is where, again, we missed all these words that mean stuff. Meatus just means a hole. It's Latin for hole. There's lots of Latin words for hole, by the way, but this is one of them. So the external hole, the outside hole that you hear through, that's literally what the name means. Again, scientists are not very creative. So the ear looks like this. Here's the auricle on the outside. Here is that external auditory meatus, or that ear canal. You've heard it called that, kind of. Yes, sir? Sure. Yeah. You mean like different earrings and things like that?
No, just like people who have like issues with their, I don't know how to explain it, but like the direction of the ear, the sound comes into the ear. They put anything on the ears like paper or tape or something.
Sure, no, you're exactly right. Our ears are basically designed as a funnel to have the sound waves bounce into the meatus, right? If I can't hear you, what do? I like this, right? I make my ears bigger so that the sound can be grabbed, and I cup my hands, right? So when it bounces, it'll go right in. If I were to do this, try it for a second. Talk with your ears like this. It totally changes how you hear. Don't you sound weird? Don't you sound different? What I hear is I hear this. It's really weird. Does that make sense? So I'm not covering my ears. I'm just changing the direction of how I hear, and it makes a huge difference. I wouldn't think so. That's what I thought Eric was talking about. I wouldn't think that should, because they don't usually change the shape per se, and the earlobe itself doesn't really do anything. It's just decoration. So, yeah. All right, let's move into the middle ear. Again, not too much happening on the outer ear. The middle ear houses what are called the auditory ossicles. It's the little bones that are in your ear. They have three names: the incus and the malleus and the stapes. Those are the Latin words for them. Here's what they look like. And yes, they really are that small. Like that's a penny. And those are all three bones on that penny. Tiny little bones, right? What's the point of these guys? If you look here, here's where they are. They're connected to this tympanic membrane, or what you might call the eardrum, right? And then you have the malleus and the incus and the stapes that stapes attaches into the cochlea on the oval window. Anybody have any idea what their point is for? Okay, to hold stuff in place. I got you, kind of a space filler. It does have some support piece. To send vibrations. So they're actually transmitting the vibrations of your eardrum into the cochlea. That's correct. There's also one more function it does. It does transmit, but it does something else as well. It amplifies. And here's why. Let me show you just a quick, terrible picture. Because I'm not a drawer. My wife is the drawer. I'm not the drawer. This is your eardrum. Oh my goodness, not earbrum. That's what I get for writing the regular name. We should call it the tympanic membrane. Okay? And I'm exaggerating. It's not actually that big in your ear. Okay? But the oval window is about this size. So what we're doing is we're taking this large area and we're moving it to a small area. If you know anything about how waves travel, if you go from big area to small area, the waves get larger. It amplifies. It makes them louder. So it allows little tiny vibrations on that tympanic membrane, the outer membrane, to be able to translate into something that you can hear. Does that make sense? And what connects these are those three little bones. Sir?
So you said it's louder if it goes from a big.
Right. Mm-hmm. It'll amplify it. If you take something that is small and make it big, it dampens it. It makes it less intense. Like right. Just simply the physics behind the proportions, yeah. So what you're doing is you're directing the sound in a specific area. Does that make sense? You're taking, instead of when I speak, my mouth, the vibrations are going everywhere. If I put a cone on it, I'm sending all of my vibrations straight at you. I hear what you're saying. Why don't then, if you were to come on just the other side of that, if I were to flip it over and put the big end on my mouth and your ear right next to the small end, it would sound louder than if I was just speaking at you like this. Because it's taking all of those waves and focusing them into one small spot. We do this more for direction, not for amplification. Does that make sense? That's good. I like what you made me think there. It's good. Yes, ma'am. Ossicles means bone. Yep, os, anything with os is telling you it's bone. Okay, let's keep rolling. We got a good bit of stuff to go here, but good questions. Here's my oracles, or excuse me, my ossicles. Here's what they look like by themselves. Malleus, which means hammer. Incus, which means anvil. Stapes, which means stirrup. And they kind of look like that, don't they? Not really, but kind of, sort of. Incus is the anvil. So they, again, go into the oval window, amplify, and again, this is a key point right here. They transmit and amplify sound, right? That's the key behind those ossicles. That's why we have them. All right, the auditory tube, again, that's the eustachian tube. I keep going back to this picture. I wish I should have put it more places on the... Here's the auditory tube. We're now into that inner ear. So outer ear, middle ear. Now we're in the inner ear. What does the auditory tube do? It's a connection. Oh, good. It maintains the pressure. That's exactly what it is. It maintains it by having a connection into your throat. You've been on an airplane or going on a mountain drive and your ears get clogged, right? And how do you get the pressure to equalize? You swallow, or if it's really bad, you like hold your nose and kind of blow out. You can actually blow air up into that inner side of your ear. Yawn is another way. Yes. And what that's doing is it's trying to equalize the pressure. So that's a good thing. The bad thing is if you have a throat infection, what happens? That infection can go up into your ears. That's often how we get ear infections, is because there's bacteria in our throat and they go up that auditory tube into our ears and you get an ear infection. Well, I mean, you can't, truthfully. Yeah, your body has defenses that try, and there's mucus and stuff that helps keep that from happening, but yeah, there's not much you can do to keep it. All right, let's keep moving. So in the inner ear, we've got two pieces. We've got this osseous, remember os means bone, with a membranous labyrinth. And labyrinth just means this whole twisted set of tubes and areas, right? Let's get some pictures. Here's our inner ear, right? Can you see that looks like a labyrinth, like a maze, right? Just all over the place. And there's kind of three distinct areas we're dealing with here. The cochlea, the semicircular canals, and then this area in the middle, kind of called the vestibule. Okay? The cochlea is what actually houses the little cells, the receptors that let us hear. The semicircular canal houses the receptors for us to keep our balance. So in this inner ear are these two areas that are doing these two very distinct senses. And inside, in between, there's this little area called the vestibule, the scala vestibuli, but we just call it the vestibule, this area in the middle between those two guys. Okay? Yeah, yes, ma'am. Hearing aids, for the most part, they are just amplifying sound. They're like a microphone that's collecting the sound and then sending it right into that tympanic membrane and making it vibrate. So, so it depends. So if you're talking more of a cochlear implant type thing, which that's where there's actually a problem in the cochlea itself, actually receiving the signals. And so they have that implanted into, into the ear part so that they can hear. It's a different thing. A hearing aid is just an amplifier. A cochlear implant is actually working with the receptors themselves. Okay. Here's where we're getting into how it actually works. Is that we have these little tiny hair cells, right? So if I show you this picture, here are the receptors, the little hair cells, okay? And what kind of receptor do you think they are? Are they chemoreceptors? No, there's nothing that's being dissolved there, right? Are they photoreceptors? No light gets into your ear. Do you know how they work? They bend, right? As the sound waves come in, they bend. So what kind of receptor would that be? A mechanoreceptor. That the actual receptor is moving, and that's what sends the signal. So inside that cochlea, again, it looks like a snail shell, right? There's this fluid that's present there. And the fluid will vibrate as you're hearing, as you're listening to my voice. The fluid in your ear is vibrating. And these different hair cells are tuned to different frequencies. And when that frequency is heard, that mechanoreceptor will move, and that sends the signal down into the brain. Does that make sense? The pathway that would travel would be down that vestibular cochlear nerve to what part of your brain does hearing? What part of your brain is right next to your ears? The temporal lobe, right? That is the part of the brain where it gets sent to, where those signals get sent to. I thought in my presentation there was a better picture, but on page 286, if you want to take a look there, they show you a zoomed-in picture of the little tiny hairs that are there in that cochlea. They're tiny. I mean, look, the zoom in on that is 3,800 times, right? Almost 4,000 times zoom. So these are tiny little things. Now, when we decide to listen to our music so loud that I can hear it from across the room with your headphones on, I'm talking about me too, you can actually damage those hairs. You can break, like literally they can get bent or broken because they're vibrating so crazily that they break. And they don't heal. They won't grow back. So that's why those of us old people, our hearing starts getting worse and worse. And there are ranges of sound that I can't hear that you can. I'll prove it to you in a minute or two. Okay? And that's because those hairs on the ends, the very low frequency, the very high frequencies, they get damaged. If you want a good job for the future, go into to be a audiologist, because you all are going to have tons of hearing problems. Because there's a lot of folks who listen to awfully loud music in very close proximity to their ears. Yes, ma'am? Then you can what, sorry? And that's okay. I am deaf, yes. Sure. Oh yeah, certainly. You can get better at those receptive pieces, yes.
So, like, I know whales and dolphins
Shh.
communicate in different frequencies.
Mm-hmm.
So in their ear, do they have like
I would assume, I don't know anything of their anatomy, but I would absolutely assume they have a very similar something. Yeah.
Can we train our ears to hear things?
Well, there's a certain frequency range that our ears use that if it's beyond that, no, we can't. Like, we just don't have the right hair cells to hear those frequencies. Potentially, sure. Yeah, potentially.
Do different size people
Shh.
have different size hairs or different amounts?
That's a great question. I wouldn't think the amount would vary too much. It's not like I have longer bones because I'm taller. I don't think I would have more there. No.
But is it like the size? Your hair, like if somebody
I wouldn't think. I think our cochlea should be similar sized. Maybe proportionally a little larger, but I don't think that makes my hearing better. It's a good question. I don't know the answer to that one. It's a good question. All right, let's try something here. Shh, 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 shh. So I'm going to play some sound here. Let me just get a bass line. Oops. Just turned her down just a little bit. This is just simply an online tone generator. Shh, shh, shh. I'm assuming you all can hear that. If is that still too loud? Are you okay there? So, in case you're a musical person, that's a C6. That's a 1,043 hertz. Now we're down to a B. That's a C sharp. It's getting quieter though, right? You feel it, right? You can feel that kind of vibrato. Now, these aren't tremendous speakers. But are you comfortable right about? I would imagine these speakers have a low range of 50 hertz. Every speaker has a range of frequencies it can produce. Below 50 is where these speakers die. Most of us, that's about where our hearing would stop as well. You wouldn't be able to hear much more below that. Okay? I could crank the sound way up. We might hear a bit. I don't hear much. Oh, a little bit. Now that I say that, because that's really loud. Okay? I'll turn her back down. Let's go the other direction again. That's still really loud. I'm just going to turn it down a little bit. I'm going to tell you right about there, for me, that's the end. Not really. I feel it, but I don't really hear it.
You can't hear that? I feel it in my throat.
Because I'm old.
You feel it in your throat.
Can you still feel it? Still hear it?
Yeah. Okay, no, I can't. Okay, I'm done. Yeah, I can feel it. Oh, I feel it. Barely. No, it's not.
That's as high as this generator goes.
Yeah, I can still hear it. Who hears it?
Sure. So again, this is about the very edge of any of our range, about that 20,000 hertz. Sir?
I hear there are some companies that play this kind of like really high tones in front of their companies because they know that they know that the younger people will be able to hear it, so there won't be any like vandalism or anything. The older people won't get bothered by it.
Isn't that funny? I have not heard that. That would be kind of interesting. Yeah, cool. So, again, this wide range, remember that is just simply a function of those little hairs in the cochlea. When a specific frequency comes, it vibrates certain of the hairs based upon their length, right? And that's what transmits the sound on into our ears, or into our brain. Questions there? Got 6 minutes. I got to zip through this balance piece. All right, let's talk about the sense of equilibrium. 2 different types. And we're going to do a lab on this on Thursday. By the way, a couple of good labs coming for you. We're going to do a balance piece on Thursday during the Love to Learn time. Shh, 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 shh. And then Friday, we're going to do some eye dissection. We got some cow eyes that are coming. We get to do some good eye dissection. So, I don't know. I don't know. Shh. All right, stay with me, guys. I got 5 minutes. Shh, shh, shh. So 2 different types of equilibrium, right? Static and dynamic. Static is when you are standing still. Shh. Dynamic is when you're moving. You're like, duh, of course. That's what that means. But they're 2 different systems. Okay? Let's talk about the static one first. Static equilibrium, again, it happens in the vestibule, which is that area right between the semicircular canals and the cochlea. And it's actually the name of the little spaces where these are formed is the utricle and the saccule. Again, these are little expansions, little bubbles inside that membranous labyrinth. You have something called the macula, which has these little tiny hair cells and some supporting cells that are inside that utricle and saccula. It looks something like this, okay? So this whole thing is the macula, right? And inside that, there's this gel blob, like that's literally what it is, that has these little hard calcium rocks that they use the Latin for rocks, which is otolith. Like literally you got rocks in your head. Okay? This is in the ear, in the vestibule between the cochlea and the semicircular canals. When you tip your head forward, the rocks, because of gravity, fall forward, and that bends those little hairs inside the macula. What kind of receptors do you think those hairs are? They're mechanoreceptors, because they actually, when they bend, they send the signal. And that tells you where your head is in this static plane. Does that make sense? For dynamic equilibrium, we use a whole different set of structures. The semicircular canals perform dynamic equilibrium. Inside each semicircular canal is something we call a crista ampullaris. That's what this guy is right here. This whole piece is the crista ampullaris. This tiny little gel piece on the top, that's called the cupula. Shh. Attached to that cupula, again, are these little hair mechanoreceptor cells. That semicircular canal is filled with fluid. And when you turn your head, or when you're moving in space, right, you're moving around, that fluid flows. It moves, which will then bend that cupula based upon how you're moving. And your body senses that. I'll get your questions 1 second, guys. There's one thing I want you to see, though. I guess I could go back here to find that picture of the semicircular canals. Is there anything you notice about these three canals? There's something very interesting about their shape. Kind of, the way they've drawn it here, I would agree. What's interesting is that one loop is in the y dimension. These are good for my physics folks. One loop is in the x dimension, and one loop is in the z dimension. So it's covering the 3 dimensions of space that you move. So that I move side to side, one semicircular canal will sense that. If I move up and down, one semicircular canal senses that. If I move back, sorry, that's a foot, and back and forth this way, a different semicircular canal senses. Does that make sense? It's designed to get all 3 planes of motion, which I think is pretty darn cool. Okay? Whew. That's a lot of stuff for one class period. Thanks for bearing with me. I'm going to stop this. The bell's going to ring in a moment. Adios.